Okay guys, we did the first derivative test to find local and relative extrema. That was on the last video, and now we're going to talk about applications of the second derivative. So there are 4 applications thus far. The first one is interpretation. We can take a position function, which is always denoted s of t or x of t, and we can find the velocity by taking the first derivative of position, or we can take the second derivative of position, which is equivalent to the first derivative of velocity, to find acceleration. And we did one in class, I believe, today, and anyway, we'll see another example of that soon. The next thing we can use the second derivative for is to determine if a function's concave up or concave down. So we can determine concavity using the second derivative. The third thing we can use it for is finding points of inflection, or when the concavity changes on a function. We can take the second derivative, set it equal to 0, and figure out whether or not it changes signs about those values of x that we found are critical numbers that we find by solving the second derivative equal to 0. And finally, we can use the second derivative test to find local extrema. Okay, so an example of the first situation is we might have some position function given by negative, this should be a t, by the way. Habits die hard, but I'm so used to writing everything in x, but these should be t's here, so we'll just change them to t's. Kind of messy, but I can't find my little whiteout thing. And so, of course, this would be a t, right? So the derivative of 3t squared is negative 6t. So let me fix this, negative 6t. And the derivative of 18t is just 18. So I took the derivative, and I found this is velocity. And if I want to evaluate the velocity when time is equal to 1, well, all I have to do is plug a 1 in here, and I did that here. To get 12. So the velocity would be 12 when time is equal to 1 for this particular function. If I wanted to find the acceleration of this function and evaluate it when t is equal to 1, well, I just take one more derivative. So I'm taking the derivative of velocity now, or this one, this is the cleaner cut. And if I take the derivative of this term, I get negative 6, and if I take the derivative of the second term, it's 0. So the acceleration is a constant function. It's negative 6. No matter what value I plug in for t, I'm going to get out a negative 6. So even when I do evaluate this at 1, the acceleration would be negative 6. Capiche? The second case, and I already wrote on this because I recorded this earlier, but then the dog went berserk, so I had to, it was really bad, so I had to cancel it out. So I took this picture of this function here from the book. Don't remember what page it is, but it doesn't matter. Okay, and this is the function f prime, and what you're asked to do is determine where the graph of this function's concave up. Well, we can use our little table, right? We know that a function is going to be concave up when the second derivative is 0, and concave down when the second derivative is less than 0. And by the way, when f prime is increasing, we know that f is going to be concave up on that interval, and when f prime is decreasing, we know that f is going to be concave down. So when we're talking about concave up, since this is the graph of the first derivative, I just need to see where the graph of f prime is increasing, and it's increasing between negative 2 and 1, and so that's where the graph of f would be concave up. Concave down, they don't ask that question here, but it would be negative 4 to negative 2, and from 1 to 4. Okay. Where does f have points of inflection? Well, I know that the second derivative equals to 0 wherever there are bumps on the graph of f prime. So here and here they're going to project as the zeros of f double prime. And I can either sketch the graph, which I had already done, because remember, I need to see if the second derivative changes sign about those zeros. So these are the critical numbers when f double prime, or second derivative, equals 0. And since f prime is decreasing, I know f double prime will be below. F prime increasing, f double prime will be above. F prime decreasing, f double prime will be below. So it's clear that f double prime changes sign here, and so therefore I'm going to have a point of inflection on the graph of x at x equals to -2 and 1. Analytically speaking, you're probably going to be given a function and asked to find the point of inflection. Okay, so what does that mean? Well, we just said that if we want to find points of inflection, that occurs when the second derivative equals 0 and changes sign. So if the function is x cubed minus 3x squared, then the first derivative is 3x squared minus 6x. If I take one more derivative, I have 6x minus 6, and I'm going to set that equal to 0 and solve. So by solving, I got that x is equal to 1. And so it's almost like the first derivative test, sort of. You're not looking for extrema, but you're going to plot this one on a wiggle graph, and you're going to test a number to the left and to the right. So I plugged in a 0, and when I plug in 0, I get a -6. That's less than 0, so my second derivative is negatively valued, so that means the graph of f will be concave down. And then I went ahead and I plugged in a 2, and I get a positive number, so the value or the sign that my second derivative takes on is a positive, and so I know my function is going to be concave up on that interval. So since the signs change, this is the f double prime of 1 is equal to 0 and it changes sign, then I know there's definitely a point of inflection or a change in concavity on the graph of f, even if I don't have a calculator and I can't see it. Okay, by the way, whenever we plot these critical numbers on the number line, it divides or subdivides the number line up. In this case, there's only one critical number, so it subdivides it into two pieces. And this piece here goes from -infinity all the way to 1, and this piece goes from 1 all the way to positive infinity. So you might be asked what intervals the graph is concave up or concave down. Then you could say, well, it's concave down from -infinity to 1, and it's concave up from 1 to infinity. Okay, so that's number 2. Okay, the third one we already did, point of inflection, so I sort of killed two birds with one stone on that last problem. And now we've got the second derivative test for local extrema. So let's look at that. The second derivative test. Second derivative test. Remember, this is for local or relative extrema. Okay? Do we have a local max or min? So, let's see. I don't know. Let me find one. Here, maybe a simple one. So perhaps f of x is equal to 3x cubed minus 36x minus 3. I think we might have done this one in class. It's one of the evens, but it's a simple example. And what do we know about that second derivative test? Well, it says that if the derivative at a critical number equals 0, and the second derivative evaluated at that critical number is positive, then our function is going to have a local minimum. If the derivative at some critical number is 0 and the second derivative at that same number is negatively valued, then we're going to have a local maximum. And if they both equal to 0 for that particular critical number, then the test fails. And if the test fails, you got to use the first derivative test. Oops, sorry guys. There you go. Use the first derivative test. Okay? So let's see. F prime of x is equal to 9x squared minus 36. And we're going to set that equal to 0. I'm going to factor out a 9, so we have x squared minus 4 is equal to 0. So we have x plus 2 and x minus 2 is equal to 0. So x is equal to plus or minus 2. Those are the critical numbers of the first derivative. Now I'm going to take the second derivative. So the second derivative, using what's left of the first derivative here, is 18x. So that's pretty simple. And now what I'm going to do is I'm going to take each one of these critical numbers and plug it into the second derivative. So when I do that with -2, I'm going to get 18 times -2, which is less than 0. It's a negative number. Okay, so what I expect to see on the graph of f, if I could graph it and inspect it, would be that my graph would have a local or relative maximum at x is equal to -2. If I evaluate the second derivative at the other critical point, which is +2, I'm going to have 18 times 2. Again, I don't really care that that's 36. I mean, you can write that, but that's not my concern. My concern is that it's positive. So the first derivative is 0 here, the second derivative is positive, so I would expect to have a local minimum at x equals +2. That's the second derivative test. And you know, I wish I could find one where the test fails. There aren't too many. I mean, if they ask you to use the second derivative test, chances are it's not going to fail. But let's just go back. Let's just pretend it failed for a second. The rule says that if it fails, then we have to use the first derivative test. Well, you know, maybe I can use whatever test I want. So if I look at the first derivative again, which is 9x squared minus 36 equals to 0, you know, again, I can factor this down to x equals plus or minus 2. Those are my critical numbers. So all I have to do is put those on a number line and test the first derivative on the left and the right. If I test at, say, -3, I'm going to have a big positive, right? I'm going to have 9 times 9 is 81 minus 36. That's going to be positively valued. If I test f prime of 0, well, 0 minus 36 gives me a negative derivative value. And then if I test f prime of 3, I'm going to have 81 minus 36. It's going to go to positive again. This is going to be positive. So what do I know? If f prime is positive, that means f is increasing on this interval. It's going to decrease where it's negative, and it's going to increase where it's positive. So I expect a local max at x equals to -2, and a local min at x is equal to +2. So we get the same answer, okay? You know, it's a shame because if you have a crazy little function and you go through a lot of work to take the second derivative and fails, then it's like, now I got to go back and do the first derivative test. So most of the time we just use the first derivative test, but if you're asked specifically to use the second derivative test, then you must use it. Okay, second derivative test. Now, I know that there were some functions, I'm looking through the book here, that, you know, a little bit difficult to deal with. I think I covered the most difficult ones in class. And block 24, you hardly ever ask me any questions, so, you know, it's hard to gauge. Like, if you don't ask me questions, then I think you're doing just fine. I'm going to assume that because I have nothing else to go by. But